Hi there, my name is Andrew Brown, and welcome to Steps to Problem Solving. This video will teach you how to solve organic synthesis problems. Because they are so crucial for the MCAT, and because they tend to induce panic in many MCAT students, we're going to show you a step-by-step method as we work through 2 example problems and 4 practice questions. As we move through the nomenclature, functional groups, and reaction mechanics, including stereochemistry, keep an eye out for the why rather than just the how. After watching this video, you should be able to answer questions like this one, which asks you to predict the product of an organic synthesis reaction given only a reactant and the reagents. Okay, we're actually going to explain how to use the 6-step method with a couple of examples. We'll go all the way through the method with this first example, and then we'll see another example and go through it again, but a little bit faster. When we use nomenclature to determine important structures, we want to visualize the reactant given in the question stem. For more complex reactants, draw out the structure in your scratch paper. Draw 4-oxopentanoic acid by reading its name backwards. The suffix oic acid tells us we'll be dealing with a carboxylic acid. The next element, pentan, gives us the length of the main carbon chain, 5 in this case. And the prefix indicates there will be a carbonyl at carbon 4. Just count carbons and draw in the carbonyl. So there we have the structure of 4-oxopentanoic acid. Now let's see how it will be affected by the first reagent. Now we can clearly see where the functional groups are in relation to one another and make statements about their relative reactivity. The ketone at carbon 4 is quite reactive, capable of participating in reduction, substitution, and protection reactions. Carboxylic acid functional group's reactivity, on the other hand, depend more on the reaction conditions. So, let's take a look more closely at the reagents and conditions in this given reaction and try to predict what will happen next. The reagent ethylene glycol is most commonly used as a protecting group for ketones and aldehydes. And the solvents tosyl alcohol and methanol seem to support ketone protection as the likely mechanism for this first step. As we will see next, protection of the ketone is extremely important because we will now be treating with a strong reducing reagent dissolved in diethyl ether. We'll hold off on predicting the exact mechanisms until a bit later in the video, so for now, let's just move on to the third reagent, hydronium. Hydronium, or any strong monoprotic acid really, has D-protecting functionality, meaning it will protonate oxygen and nitrogen-containing functional groups, enhancing their good-leaving group character. Before we observe the mechanics of this reaction, let's return to the first step and make sure what we predicted is the most likely outcome. Remember, we said ethylene glycol is commonly used as a protecting group for carbonyls, but we have 2 here. Because the ketone is said to be more reactive with ethylene glycol than the carboxylic acid, our earlier prediction holds up. Alright, so now we're ready to put together all the assumptions we've made and predict the entire mechanism for this reaction. First, the ketone and the diol should react to form a protected ketal group. Then the strong reducing agent lithium aluminum hydride should reduce the remaining unprotected carboxylic acid to an alcohol. The final hydronium treatment functions as a deprotecting workup, and we wind up with a 5-carbon ketone alcohol. Before we're finished, however, we must consider stereochemistry. Remember, when stereocenters are involved in reactions, the MCAT will want you to keep track of the orientation that is more favorable. In the reaction we just saw, an sp2 hybridized carbon is converted to sp3. When the product has 4 different substituents attached to it, the possibility of chirality, or the existence of a stereocenter, arises. Because lithium aluminum hydride adds 2 identical hydride atoms to the carbonyl carbon, the product will only have 3 unique substituents, not 4, and will thus be achiral. So, those were all the steps for solving a given organic synthesis reaction. Now, we're going to rewind a bit and try the method on another example. First, we use the nomenclature of the reactant to determine its structure. 1-phenylpropan-2-ol has at its core a 3-carbon chain, with a hydroxyl group at the number 2 carbon, and a phenyl group at the number 1 carbon. So we just replace the name of the reactant with its actual structure, and we can move on to characterizing functional group reactivity. The aromatic ring is a common site for substitution reactions, because it is so stable as a leaving group. And the secondary alcohol has reactivity quite similar to that of a ketone. Now for the reagents. Chromic acid is an oxidizing agent that, in this example, will convert an alcohol to a ketone. Chromic acid can actually oxidize to the point of aldehyde or even carboxylic acid, but because we're dealing with a secondary alcohol here, the ketone is the only allowed product. The second reagent in this pathway is a primary amine, whose lone pair and minimized steric hindrance make it a likely nucleophile. Notice also that this second step involves a reductive workup containing sodium triacetoxyborohydride. It will operate similarly to sodium borohydride, with the 3 acetyl groups just reducing its reductive potential. Okay, let's just make sure to note we know which of the reactant's functional groups is most reactive, and then we can proceed to elucidate the entire mechanism. Because our first reagent is an oxidizer, the secondary alcohol is the more likely starting point. Now let's use those steps we've learned to predict the eventual product for this organic synthesis reaction. First, as we said, the secondary alcohol should be reduced to a ketone. Instead of 1-phenylpropan-2-ol, we now have 1-phenylpropan-2-one. Then, when we subject the intermediate to a primary amine, we now have alternate sites for nucleophilic attack. The primary amine is more likely to attack the carbonyl carbon due to lesser steric hindrance and greater polarization of charge there. What we get is a secondary amine that introduces a stereocenter. The conversion of the carbonyl carbon to a stereocenter is a common pathway for substitution reactions. In this example, just as in the previous one, the sp2 hybridized carbonyl becomes sp3 hybridized. What is different here, however, is that this change in hybridization occurs at a secondary carbon and accompanies the addition of a methylamine functional group. Now the newly sp3 hybridized carbon has 4 different substituents and is thus a stereocenter. Because there are no factors overwhelmingly favoring R versus S stereochemistry, we get a mixture of the 2 enantiomers. Okay, so that actually concludes the material review section of this video. Let's now practice what you've learned on some sample questions. This first one is the same as the first example we covered earlier. Even if you remember the answer, you might want to practice using the 6-step method here just one more time. As a refresher, the 6-step method will appear in the margin throughout these sample questions. By the way, the answer should be A. The next few questions will present some new organic syntheses, but they're still asking you to do the same thing. First, we use nomenclature to visualize or draw the reactant and identify functional groups in the process. Next, we check out the reagents to figure out the types of reactions that will occur. In this case, the bulky base suggests an elimination reaction, and the peroxy acid, MCPBA, screams epoxide formation. Now let's predict the reaction mechanism. Because chlorine is a good leaving group, elimination is favored at one of the adjacent carbons. If you were wondering how epoxide formation was possible due to the lack of pi bonds, now we have one. Then in the final step, MCPBA partially breaks the pi bond, creating a reactive epoxide ring. Therefore, the answer should be D. In this next practice question, sodium butanoxide is our reactant. The structure is a 4-carbon chain with a terminal oxide functional group ionically bound to sodium. The negatively charged oxide group is a strong nucleophile. Turning to the reagents, we have an electrophile with a potentially good leaving group in bromine, and the combination of ozone and zinc, which cleaves double bonds to produce aldehydes. The first step in the synthesis reaction is thus nucleophilic substitution, giving an ether with a terminal double bond as the intermediate. Now in the second step, ozone and zinc have a clear location to cut. One of the aldehyde products, formaldehyde, was actually given to you in the question stem, and so the other must be C. And now, our final question. This one starts with the reagent cyclopentene. The only real element of note is the double bond, which should have you looking for a double bond cleaver among the reagents. Osmium tetroxide suits that role nicely, forming glycols from double bonds. The other reagent, as we'll see in a moment, has protecting functionality. So, predicting the mechanism, osmium tetroxide cleaves a pi bond to yield a glycol. Notice now that we have one of the reagents in a typical ketal formation reaction. Looking at the second reagent, there's our ketone. Thus, the functional product of this synthesis reaction is a cyclopentane ring with attached ketal. B is the only answer that matches. Okay, if you got all those questions right, congratulations, that's no small feat. If not, feel free to watch this video again as many times as you need. Before you finish, take a moment to review each step in the 6-step approach we learned for solving organic synthesis problems. You got to know your nomenclature so you know what the reactant looks like. You got to identify the relevant functional groups and how they will act in common reactions. Identify the reagents involved in the problem and predict what types of reactions are likely to occur. Then determine the most reactive functional group in the reaction, which will likely be the site of the first step. Repeat steps 4 and 5 for each subsequent reaction in the pathway, and then determine if any stereochemistry has been altered. As we saw, oftentimes when sp2 hybridized carbons are converted to sp3, a change in stereochemistry will accompany. Thanks very much for watching, and good luck in your continued MCAT study.